Hey everybody, welcome back to another episode of Vision Basic. It's been a number of months since my last video. I've had to slow my pace a little bit because my time has become so divided lately. But for the past 3 or 4 months, I've been working on the source code for the user-defined command that this video is focused on. Sadly, I had to pause my work on version 1.2 of Vision Basic in order to work on this. But I'll get back to working on version 1.2 shortly. I plan to work on a news video after I wrap this one up, but not immediately. And then I hope to start a video series in the new year. I was originally going to do a video on how to play a SID file in Vision Basic, but I realized that I might want to create my own SID file first to help avoid any kind of copyright issues involved with using someone else's file. A customer of mine mentioned the program SID Wizard, and so I downloaded it and tried taking it for a spin. Well, I found it a bit unintuitive. I realized that if I was struggling to learn the ropes of this software, then my customers were probably going to struggle as well. I'm sure it's an awesome program, but my brain just has a difficult time figuring out how to use it. I might come back and give it another shot some other time. And perhaps I'll revisit this topic again for a future video. If any of you have any suggestions for a SID creation tool that I might find easier to learn and use, please leave your suggestions in the comments. I'd prefer something that allows you to relocate SID files to any memory location of your choosing. Anyhow, after a number of days of toying around with the software, I decided to pursue a different topic for my video. So which direction did I go for this video? Well, a customer of mine mentioned that the Commodore 128 has a command called play. I've never programmed on the Commodore 128, so I looked up the command in its user manual. Anyhow, it seemed simple enough, so I set out to create my own version, and I also wanted to make some improvements. Now, one reason why it took so long to create the code for this is because I programmed most of it in assembly language. Well, assembly language is a bit harder to debug, for one thing. Or debug. I ran into all kind of bugs along the way. I could have whipped up a basic equivalent first and then converted each line over to assembly language, but I wanted cleaner code. Plus, I had to employ an interrupt for playing the music, and you can't use basic commands during an interrupt. And another thing that made the process take so long is that I would change my mind about some things, perhaps move some code around, and I really didn't have the whole thing figured out when I started coding. For the longest time, I was just programming and not being able to run any of the code. The first time I did a test run, I had no audible music coming out of the speakers. But after I figured out the problem, I was shocked at how well my code actually worked. Granted, there were still some bugs in the system, but it was a neat experience to see things finally working after days of coding blindly. So, one of the things I wanted to employ was a kind of holding area for the song data. Each use of the play command would add more song code to the holding area. I wanted there to be 3 areas of code data within this holding area to cover the 3 voices made available by the SID chip. After the user adds more code, I wanted the existing data to be able to be shifted around to make room for it. I wanted the user to be able to pick any voice at any time and add any number of codes they want. And I wanted them to be able to shift around from voice to voice if they want. I also didn't want the process of adding song data to the holding area to seem sluggish, so that's why most of the code I wrote is in assembly language. Okay, so I'm going to load up a demo of sorts that won't appear on the disk image supplied with this video. The purpose of this demo is to show you one of the methods I use for debugging, which is basically to store data to the visible text screen for examination purposes. I have earlier drafts of this program that sent different types of data to the screen, but this version essentially stores the entire song to the screen, and thus the screen is being used as the actual holding area. And now here we go. Load, play demo 1. Lister, 400. This is most of the song with the exception for a couple more lines of code. When you use the play command, you first specify which voice you wish to enter music for. I chose to start with voice 3 because I wanted to see how quickly the data for voices 1 and 2 could be inserted into the holding area, since the data for voice 3 is stored at the end. The data for voice 1 will push the data for voices 2 and 3 higher up in memory, and the data for voice 2 will push data for voice 3 higher up in memory, within the holding area, of course. And some people say data, but it's alright, I don't care. We can still be friends. The second parameter, right here, indicates whether or not you wish to start playing the data. Most of the time, you'll be keeping this set to 0. You'll want to have the entire song stored to memory before you start playing it. When you are ready to start playing your song, you simply tell the play command how many voices to start playing in this second parameter. If you only want to play a single voice, you use a value of 1. If you want to play 3 voices, you use a value of 3. Sounds simple enough. If you only want to play 2 voices, it gets a little tricky because it'll start playing the voice at the start of the play command, followed by the next voice below that. So voice 1 will play voices 1 and 2. Voice 2 will play voices 2 and 3. And voice 3 will play voices 3 and 1 because it wraps back around to 1. Again, this happens if you select to only play 2 voices. Okay, let's go ahead and find out what song this is. Keep in mind that the data is going to be stored to the visible text screen. I'm going to let the entire song play before speaking again, so we'll press the key once it starts. Don't mind this up here. Now again, I'm going to just let the whole thing play. Okay. Now, you know what's funny is that actually sounds different on this computer compared to my laptop. Okay, so with this demo, I have it set up to pause the music when I press the Y key. I can pause and unpause as many times as I wish. And... alright, anyways, you get the point. Another thing you'll notice is the blue bar rising up in the border area. And I'll have to demonstrate again here. Right here. This just indicates when the song playing interrupt is happening and how long it takes to play the necessary notes within a single screen refresh. The blue line moves up the screen because the play command piggybacks the keyboard scanning routine, and since the keyboard scanning routine also updates the system clock, it needs to be accurate. So it's not going to interrupt exactly at the same scan line each time. This is much more evident on PAL systems, by the way. You won't see this blue line in your own programs. I only put it in here for testing purposes. Another thing you'll notice is the buffer area at the top of the screen, right here. The first 80 characters of the song storage area are used as a buffer to hold a line of converted song data before it gets copied into the main holding area, which is right here. As a string of user data is converted from one format into another, it is copied into the buffer. Since the converted data might not be the same length as the source data, we don't know how long the new string of data will be, so we can't just cram it into its new spot without knowing how long it will end up being, and thus the buffer. And finally, the dancing color bars here are meant to be a diagnostic tool, allowing you to visually see if all of your notes are hitting at the correct time. If 2 or more notes are supposed to hit at the same time, you'll see it happen here. Or not, if you goofed up somewhere. When a rest is encountered, you'll see a note moved off to the right side of the screen. The blue note here spends most of its time resting. Lucky guy. Another feature of this software is that you can enter different songs into the holding area. You can't have 2 songs in the holding area at the same time unless you wish to play them in succession. But when you want to enter a new song into the holding area, you don't have to worry about clearing out the old data. I'll demonstrate this by having the same song fed into the holding area, and the existing data ends up being overwritten and or shoved out of the way. So just watch the screen for a minute here. And do it again. Okay. When it comes to song selection, I needed something simple because I didn't want it to take me forever to convert a complex song into lines of code. As it is, I am hoping that I got all the notes right. The song sounds like it's playing right. So I already had this song in my head, but I didn't know the name of it. I had to listen to anywhere from 100 to 200 short clips of classical music before I stumbled upon this song. It is called Minuet in G major. Now I want to show you a slightly different version of this song. Oops. The main difference here is that I have the song entered in voice order, which does speed up the conversion process. This reduces the number of bytes that need to be shuffled around. Now before I run it, I'm going to go ahead and change the instrument and see if the piano sounds a little better. You guys can be the judge. And change that one. And this is kind of a sneak peek, but we're changing the instrument. Okay, now the main thing I just want you to see is the speed at which the data gets re-entered into the buffer. Or not the buffer, well, you know, the song playing area. And I'm going to warp mode this so we don't have to wait as long. Okay. Okay, now watch how much quicker the data gets fed into the holding area. And one more time for those who missed it. Okay, so for the rest of this video, I'm going to read pretty much what's in the manual that comes with this package. So I might end up repeating some details, but that's okay. Alright, let's go over the different codes and instructions available to you. And let's get out of here. And I'm going to copy something to the screen. And this is just the format for the command. You will typically build a song in pieces using codes or instructions. The play command itself converts your codes into a format that the music playing routine can more quickly interpret. An area of memory is set aside to store the converted codes. I've briefly mentioned the holding area for these codes, but you must pick an area of memory that won't come into conflict with the other areas of memory that your program might employ. If your music ends up being stored under the kernel ROM, for example, you won't be able to put a bitmap screen there. There are 4 different versions of the Play software. 2 of those versions store song data in the area from 49152 to 53247 as such. and the two others store song data under the kernel, which starts at 57344, I think. And again, you can only build and play one song at a time. In order to play more than one tune, you will need to clear out the previous music and feed new codes and instructions into memory. This process is generally not too time-consuming, as you've seen, and might only take a second or two. The software includes two different sets of frequencies for music notes. One set is for PAL computers, and the other is for NTSC computers. So let's go over the different codes and instructions you can use to make music with. I tried to make things as simple and intuitive as I could. First, you specify the voice that you wish to store music for, right here. Choose voice 1, 2, or 3. You can build your song one voice at a time, or you can build with any number of notes and hop around from voice to voice as you wish. You'll need to keep track of things though, because notes are added in precise order for each voice. You'll have to make sure that everything synchronizes when all is said and done. You could add 10 quarter notes to voice 1, 5 half notes to voice 2, and 4 eighth notes plus a half note plus 6 quarter notes for voice 3. And they should all reach the same point in a measure at the same time after playing all of those notes. As an example. Anyhow, for each use of the play command, you can only work with one voice at a time. Okay, so you'll first pick which voice you wish to enter data for. So we're just going to do an example here. We'll just go with voice 1. We're not ready to start playing the song yet because we just started, so we'll put a 0 as our next parameter. Now, if you've entered all of your song data and you simply wish to start playing your song, you can enter a value from 1 to 3 and simply stop here. You won't need a third parameter. Now comes the fun part. You could start entering music notes, but you might wish to tell the player which instrument you want to use for the voice in question. Each voice can have its own instrument, and you may need to specify an instrument for each voice if you don't want piano chosen for each voice, which is the default. You can also change instruments at any point for any voice if you wish. There are other settings we can toy with here at the beginning, but I'll explain those later. Now, because the third parameter for the play command is a string, you can substitute a string variable if you wish. This allows you to build strings of codes and instructions, combining various elements together. You can use the same string multiple times, but change a value within the string before each use, for example. So how do you enter music notes? That's the big question, right? Well, you simply type any note from A to F. And heck, we'll just go with A. Notes actually run like they do for piano, so the octave starts with C and ends with B. So you'll find this A note near the end of the octave. And to be honest with you, I'm pretty sure I had a music teacher at one point who said Octave, and that had been the pronunciation in my head for all of this time. So I'm going to be good, and I'm just going to say octave. I don't want to, but it's okay. We can still be friends. If the note needs to be sharp or flat, you'll have to indicate this next. Use the number sign or hashtag or plus sign for sharp notes. So either this or this. Oh wait, this. And use $sign or the minus sign for flat notes. $sign. Wait, sorry. Or minus sign. There you go. Now, the reason I included the plus and minus is, again, for the sake of trying to be intuitive here. Now, the number sign also makes sense, but the $sign is kind of like, well, that's what the play command for the Commodore 128 uses, so I just stuck with it. There's really nothing else that looks like a flat, so that I'm aware of, so hey, we'll just go with $sign. But for this demo, I'm just going to go with sharp. Alright, next comes duration. If all you need is a quarter note, you simply type your chosen note, like this, that you see here, and you're done. You don't need to add a duration of any kind. But for other durations, you'll need to add a letter or a number. Now, the following letters are just pretty much copied from the play command for the Commodore 128. So use W for whole note, use H for half note, use Q for quarter note, which is unnecessary, use I for eighth note, sorry, but E can't be used because it's an actual note, and use S for 16th note. I personally don't like using the letters, so I added numbers to the mix as a more intuitive alternative. With numbers, just think denominator. So 1 is for whole notes, 2 is for half note, 4 is for quarter note, and again, unnecessary, and 8 is for eighth note, and 16 is for 16th note. I personally find this system much easier to interpret visually. Otherwise, it just looks like a big old jumble of letters and no numbers. Okay, so for dotted notes, simply add a period. Yay! After the duration, of course. So putting all of the pieces together, you might want to play a D-sharp dotted eighth note, and it would look like this. Back. D-sharp eighth dotted. Now, in the demo, I crammed all of my notes together, but you can put spaces between your notes for better readability. An error will be triggered if you place a space between the D and the number sign, though. So don't do that. Yeah, don't do that. So I recommend just using spaces to space out the notes and instructions. Sometimes you'll see notes in sheet music that are joined together to create strange durations. Maybe you'll see a half note plus a 16th note joined together. Well, that's what the asterisk is for. Type an asterisk and follow it by a duration expressed as the number of 16th notes you wish to play. So in this example of a half note plus a 16th note, you'll type asterisk 9. And we're going to fix this. All right. Now, the reason for the 9 is because a half note is 8 16th notes, and you need to add one more 16th note to the mix for a grand total of 9. Anyhow, use this notation in place of the note values described previously. That is, if you want, weird durations. There is no symbol you can use to join notes together with, so this is the solution in place. And if you need something a bit more specific, you can also specify the number of jiffies to play a note for. Just type an exclamation point followed by the number of jiffies you need the note to play for. And a jiffy is 1/60th of a second. So, exclamation point, 54. And I think that's the same as, I think I chose 54 because it should be the same as this. So. And what about rests? Glad you asked. Simply use R instead of a note, and follow it with the same timing codes that you would use for musical notes. So, RH would be a half rest, for example. The play command treats rests as if they were notes, but a note is simply not played. You also have a special type of rest at your disposal, a rest that plays out for the remainder of the measure. This helps to simplify things for you. So if you play a quarter note at the start of a measure and want to follow it up with a rest, you can simply type M for measure after the music note. For example, CM will play a C note, and the remainder of the measure will remain quiet for the voice in question. Okay, so let's move on to the rest of the controls at your disposal. To change the current octave for a voice, you simply type O and follow it with a value from 1 to 8. And I'm going to put it up here. And we'll go with 6. And move that back on. The play command for the Commodore 128 uses values 0 to 7, I think. But I don't like starting things off at 0, so I chose values 1 to 8 instead. Middle C starts in octave 4. I provided a reference image with colored notes and such that should help you to figure out which octave value you need to use when playing certain notes. You can also use the less than symbol to lower the octave by 1, or use the greater than symbol to raise the octave by 1. So to play a C note that is an octave lower, an octave lower, do that. And if you want to go back, because you're going to raise it back to where it was, do that. Now you can also use multiple symbols for lowering and raising the octave as needed. So you can also do G, as in gee whiz. If the octave goes out of bounds, an error will result and your program will halt. And if you change the octave for one voice, it will not affect what happens in the other voices at all. Okay, what about instruments? If you wish to change the instrument, just use in followed by a value from 1 to 16. Now I has been taken, so now it's in for instrument. I copied the 10 instruments from the Commodore 128 version of the play command, but I also chose to shift the values here. So the piano instrument starts at 1 for my version of the play command instead of 0. I added one bonus instrument to the mix, number 11, which is the instrument you heard at the beginning of the video, and it's similar to the piano, but you can add more instruments if you like in the source code, or you can even modify the existing ones that are there to whatever you like. The manual explains how to do this. You can switch the instrument at any point in your song, and you'll want to change the instrument for each voice starting out if you don't want to go with the default of piano. And I probably mentioned this twice already. So, let's back up a little bit. And, I don't know, we'll go to here. Okay, so for piano, it's in 1. For the accordion, it's in 2. For the, I don't know, is that calliope? I should have looked up pronunciation. For drum, which I really don't like the drum, 4. And for flute, it's 5. For guitar, it's 6. For harpsichord, it's 7. For organ, it's 8. And for trumpet, it's 9. And xylophone is 10. And of course, the instrument you heard at the beginning of the video is 11. And it could go up to 16, but there are no instruments set up for those, so make of them as you wish. Now let's talk about volume. If you want to change the volume, just type V and follow it with a value from 0 to 15. So we'll just say 7. In this case, I did keep 0 in the mix because it turns the volume off completely. So yeah, you can turn the volume off completely. You won't be able to hear your song, but hey, there might be some weirdos out there. And again, you'll be affecting the volume for all voices. I did add some codes to allow for more dynamic volume controls. For example, let's say that you want to fade the same section of music to 0 as it repeats. You can use V plus to increase the volume by 1 point, and you could use V minus to decrease the volume by 1 point, and you could use V divided by to divide the volume in half, and you can use V multiply to double the volume. You can also adjust the volume between each and every note, but again, all voices will be affected. Alright, let's cover tempo next. You can adjust the tempo anytime you want, but it will affect all voices. So you'll want to feed the notes for all voices into memory up to the measure that you want to adjust the tempo for. And for parts of your song that repeat, you can't alter the tempo for notes that are already stored to memory. Durations are stored to memory as jiffies, so they're set. In other words, if you speed up the tempo and jump back to replay a section of notes, those notes won't play any faster. Anyhow, to change the tempo, you type T and follow it with a value from 1 to 64. The tempo value sets the number of jiffies for a 16th note. The default is 6, so a 16th note lasts 1/10 of a second by default. Now let's type in a small demo that shows how to change the tempo, but also how you can manipulate the string for tighter code. Alright, 104, D equals 18, 2, 3, step, -3, 3. 110, S dollar equals T for tempo, D, that's the value for the tempo, and octave 4, C, D, E, F, G, A, B, and then we're going to raise the octave for the following C. Hopefully I'm typing this in correctly. 120, play this string that we've just created. 130, next. 140, play voice 1 and only 1. And 150, key press and end. And again, I'm going to warp it. Alright, listen up. Alright, there you go. And that's how you can change the tempo in a dynamic fashion. Alright, next we're going to talk about looping. If you want to have a part of a song repeat, you place a P in the spot where you want the music to jump back to. P is for position. And then you issue a loop instruction. And type 100, play, 2, 1, P, C, G, C, B, C, G, C, E, L4. C, G, C, B, C, G, C, E. Okay, I think I did that right. And here's the P I mentioned before for position. And this is the loop. And it's going to jump back to here 4 times. Or I'll play this part 4 times. It's actually only going to jump 3 times. To loop back to the chosen position, type L and then a value indicating the number of times you wish to loop back. So L4 in the song here will play your selection a total of 4 times. To have things repeat endlessly, type L0. But we're not going to do that because we don't have time, right? Okay, so run. Warp it. Alright, here we go. No, that's not exactly the prettiest melody. It's supposed to be a C chord with an added 7th. Not exactly the prettiest thing, right? Alright, let's stop it. You can have multiple sections of a song repeat, but you cannot have nested loops. Now, if you want to loop back to the start of your song, you don't need to place a P at the beginning, since loops will loop back to the start by default. You will need to use P and L for each voice typically. But you might have a measure or 2 in the bass, for example, that might repeat several times, while the top voice or 2 are meandering from measure to measure. In this case, you can have the bottom measure or 2 repeat the number of times that are necessary without the upper voice or 2 repeating in any fashion. If you have some music for a game that you want to repeat over and over again, you can also use the jump instruction. Use J to do this, and it will cause your song to repeat over and over again from the start. Unlike looping, you don't specify a position to jump back to. Jumps always go back to the start of things. One benefit with jumping is that it allows for a type of nested looping. You simply do your looping on the inside of your song, and you issue a jump at the end so that the entire song plays repeatedly. If you have a loop that jumps back to the start, and then you also have a jump that also jumps back to the start, you might need to place a position marker at the start of the score. The Minuet example song has 2 loops, and it also repeats endlessly, but I discovered that I needed to place a P at the start for each voice. Anyways, as an example, 100, play, P, C, D, E, C, wait, I thought that was a 13, L3, B, A, B, 2, J. I was originally going to paste these in here, but let's see if they're, if I'm typing them in correctly. Okay, anyways, this is an example of involving a nested loop within a jump. So this part here plays this part 3 times, and then this part plays, and then it jumps back to the start. So just to show you what it does. Now, because we only have 1 loop in this melody, we can remove the P at the beginning, so we can actually remove it. We only have 1 loop. And to demonstrate, and I think that covers all of the codes and instructions available to you. If you want to play triplets, you can use a duration of 3 or 6 as long as your tempo is divisible by 3 or 6 for both values respectively. Let me paste in an example involving a triplet. The triplets are in line 110 right here, followed by 2 quarter notes and a whole note. The first 3 notes, C, E, G, will play out in the time it takes to play 2 quarter notes. Speed. And I'm going to paste in a variation that plays 3 notes in the span it takes to play a whole note. So let me list 110 again. So here you see C6, C6, no, I'm not C6, E6 and G6. These are actually basically 6th notes. And they're played, all 3 notes are played in the span of a half note. And the next thing I'm going to paste in here is going to play 3 notes C, E, G here. They're going to be 3rd notes, and they're going to play in the span of a whole note. And again, keep in mind that the durations expressed here relate to the denominator of the note. So again, the previous example plays the equivalent of a 6th note, and this example here plays the equivalent of a 3rd note. All right, let's go ahead and play it. Okay, let's talk about the other commands available in this package. Here we have the playset command. This command allows you to access some player settings. If you want to make changes to these settings, make sure to do so before using the play command. And here you can set the volume, the tempo, the beats, and the start and end of where the music is to be stored in memory. And I'll go over that again here in a minute. And I'm going to paste in something with some values here so we can observe something a little bit better here. Okay, The tempo and volume are accessible via the play command, but here you can also set the beats per measure and the place where music data gets stored for playback. And again, I'm repeating myself. The default setting for the beats is 3. That's just because the minuet song is 3/4 time. But you can set it to 4 as well. For signatures with 6/8 timing, just go with 3/4 timing. Beats are always going to be quarter notes unless you wish to go into the code and change it yourself. Setting the beats per measure is really only needed if you're going to use the M code. Otherwise, it's really completely and utterly unnecessary to worry about it, really. As for relocating the area for music storage, you can place it lower in memory, but you run a higher risk of running into program storage, variable storage, and string storage. The minuet song uses only 526 bytes of storage, counting the buffer, so you will probably only need to increase the size of the storage area if you get an overflow error. It might be in your best interest to actually decrease the size of storage when you find out how much storage is being used after all is said and done, to help make room for other things. You might wish to push the start up to a higher value, for example, but you might also want to put some kind of graphics data in the area from 49152 to 53247, which is the default, so moving the storage would make sense there. And in my example here, we have 32768 to 40959. This is moving it lower in memory, and again, this carries a higher risk of running into program storage and variables and stuff, so I recommend just pushing it high up in memory as much as you can, or placing it under the kernel. Alright, next command in sequence here, we have the play pause command, and the yes is for yes or no. This command has a single parameter and allows you to pause the song that is playing. Set the parameter to 1 to pause your song, and set the parameter to 0 to resume playback. The only thing this command actually does is restore the key scan pointer to its default value during the pause. If you have any notes playing that are paused during the sustain part of the cycle, you might want to temporarily reduce the volume during a pause. Otherwise, you might find the constant tone or tones annoying. And if you want to play more than one song in a program, use the play clear command to clear out the song storage. Then you can proceed to funnel your next song into the storage area using another set of play commands. The next command in the series here is play stop. To stop a song from playing, use the play stop command. It pretty much works identically to the play pause command, but it doesn't require a parameter, and it shuts off the volume. It doesn't attempt to close any gate bits though. The reason for this is because you might be using the output of voice 3 for random number generation, for example. If you don't want the volume shut off, you can use the play pause command instead and manually clear out whatever sound registers you need to clear out. For example, you might have sound effects being played in the unused voices, and you might wish for them to keep playing. Now, here's something new that I never thought about trying, and yet the idea hit me like an epiphany. In Vision Basic, commands can actually double as functions. In other words, values can be returned back to the programmer. Check out what I did. I'm going to need to load up a different version of the program. The demo in memory here actually uses an unfinished version of the software, so if you want to know how much memory your song is taking up in the song storage area, you can supply a variable at the beginning of your final use of the play command, turning it into a user-defined function. It would look something like this, and I'll insert all of this. This is our example from earlier, but with modifications. We've turned our command into a function in line 110. As you can see, the variable here with the equal sign. The variable mem is the recipient of the value passed back from the routine. If you were to print out the value of mem, you will discover that the song takes up 108 bytes of memory, of which 80 belong to the buffer. So the song really only uses 28 bytes of memory, and I'm talking about this song right here. 6 of those bytes include 3 termination bytes and 3 bytes that set each voice to piano as the default instrument. And we'll run it, warp it. See, 108 bytes. By the way, if you use the versions of the software that show the visual keystrokes, the vlist command will show garbled data if you use that command after running your program. This is because the character set gets copied into the area of memory used by vlist, so be prepared for the horror. See, this is all just garbage. If you need to list the program variables, first compile your program without running it, and then use vlist. So let's do that. Enter, compile, compile. And now you can do vlist. And we'll just stop it there. Since there is no way to design a key signature, you'll have to sharpen or flatten all notes manually. But you can go into the source code and alter the offsets in line 60298. By raising or lowering the appropriate values here, you could effectively produce a kind of key signature. The values in line 60298 correspond with the letters A through G. For our example song Minuet, we could accomplish G major by changing a single value. All F notes are sharped in G major. So we could change the 6 in line 60298 to a 7. This moves the F a half step higher. Sharps increase numbers by 1 and flats lower them by 1. So just to show you, F sharp, we're going to sharpen the F right here. And so this is A, B, C, D, E, F, and G. For extreme high and low notes, changing these values might push them outside of the range that the SID can handle. So you might see an error message if you try to play any extreme high or low notes. If you want to add instruments or edit existing ones, you can alter the values in lines 61850 to 61880. And I'll list those. The values here are in hexadecimal. I don't like hex values, but they work better here. The attack and decay values are in line 61850. And that's why you got A and D. The first digit of each hex value is the attack value, and the second digit is the decay value. Both range from 0 to 15, but in hex. The sustain and release values are in line 61860. Sustain, release. The first digit of each hex value is the sustain value, and the second digit is the release value. Both range from 0 to 15. The waveform values are in line 61870 right here. Only the first digit matters, and the range is from 0 to 15. So just pay attention to the first value, not the 0. And the pulse values are in line 61880. And that they're only useful if you're using the pulse waveform. And they range from 0 to 15. Each value on each line is in instrument order. So the first value on each line only pertains to the piano instrument, for example. So this one, this one, this one, and this one. You'll have to count out from the start of each line to access other instrument settings. When it comes to hexadecimal digits, digit values 0 to 9 are the same as they are for decimal values. In other words, 9 equals 9. To represent values 10 to 15, use A for 10, B for 11, C for 12, D for 13, E for 14, and F for 15. And this is all in the manual. I might modify the code if I have time, to improve it, of course. The player I've created isn't intended to match the quality you'll find in SID music. I don't have the expertise to pull off a lot of the fancier stuff you'll find in SID players. But for simple songs that don't need to sound all synthetic, the play command should work well if you simply want to toy around with tunes, or if you want to add some music to a game you're making. Anyhow, we've reached the end of this video. As usual, I thank you all for watching. Please like and share my video, and definitely subscribe for more similar content. And make sure to visit visionbasic.net.